Hi, I'm Paco, and this is Just Enough Math. So for introduction, getting started here, I'd like to talk a little bit about who this is intended for and how we're going to do the workshop. The material here is intended to provide a hands-on introduction to advanced math for business people, particularly about how to take advantage of big data, open source frameworks for big data. There's a lot of advanced math that gets used, and it's really useful to understand why you'd want to do that in business. For the workshop here, we're going to focus on using code examples in Python. But it's going to be really brief code snippets in Python, the kind of thing that you can just cut and paste into a prompt. And we'll have a lot of illustrations and all to show what the code is doing. As far as prerequisites, this is really geared towards having high school Algebra 2 as a prereq. So not a lot of calculus, not a lot of fancy math to start out with. But we'll pick up from there, have a little bit of a refresher, and then move off into some of the areas that are really beyond calculus. The other prerequisite for this is to have some experience in business. We're going to be talking about advanced math being applied in the sense of open source frameworks with big data, cluster computing, machine learning, etc. But really, it's important to know why you're doing this in the first place. What are the business needs that are indicating certain use cases? So having that experience is very crucial. Because of many commercial successes based on big data and machine learning and cloud computing, data science, etc., there are really good business use cases for having just enough math. And there's a lot of great open source tools that we can take advantage of. I find that when I'm out teaching workshops, talking at meetups, etc., that people who are in business roles have a general need to understand more about the math, more about how to leverage, graph queries or sparse matrices, or how to do work with Bayesian statistics, etc. So we're going to cover those kind of topics, and they're very, very useful. I also want to stress that these topics aren't particularly difficult. This is kind of a sore point for me because I have a math background. And even when I was in grad school, I felt like the math was unnecessarily complex when it was being presented to people, when we were going through instruction. The other thing I've found teaching both computer science and math over the years is that, there's this kind of bar that's established by calculus. People go into college and they start taking math courses and there's requirements, but there's this point where everybody kind of comes up to the bar. And not a lot of people go beyond, 2 or 3 years of calculus that are required to go off and do the more advanced things later on. And I think that needs to change, because really the calculus is there to turn math into a kind of weeding grounds, a kind of filter, if you will. Back in the Cold War, there was big priority to have a lot of mechanical engineers building missiles and things like that. But those priorities have changed. And nowadays, in business, people need to understand complex social graphs, supply chain optimization problems, and we need to be thinking at more of global scale. We need to be thinking about really, really large-scale data problems. Issues like Internet of Things is now introducing orders of magnitude more data. So people who are working in business need to be able to contend with that and find really effective open source solutions. And that's what this math is about. As a kind of instructional rubric, we're going to work with what's called computational thinking. We'll give a little bit more background on that, but that's kind of how we're focusing in on learning and abstracting out the things that are being provided in the material. And also along the way, I hope to provide some historical perspectives, some vignettes that show the people who invented different things. Who were they? When were they doing this? Why were they doing it? What's the context? So if we can establish more of the historical context for some of these concepts, then it helps to understand how to apply them in your own daily life. So computational thinking, what's that? The idea of this, I'll quote from Carnegie Mellon University, the impact of computing extends far beyond science, affecting all aspects of our lives. To flourish in today's world, everyone needs computational thinking. So this is a big program at CMU. Google also has a big initiative for it, and we're using this more and more in the conferences, certainly at O'Reilly as well. But the big idea is that you've got reading, writing, and arithmetic. We're going to add computing right alongside that. And there are some excellent resources available. If you go to CMU, there's something called the Center for Computational Thinking. At Google, there's also Exploring Computational Thinking with a lot of great Python examples. And actually, if you are an instructor, you teach classes along these lines, Google has some great instructional materials online to use. Okay, so computational thinking. There's really 4 points here that we're going to cover over and over, and we'll use those to try to understand the math and the programming that goes along with it. The first one is called decomposition. Basically, take a complex problem, decompose it into parts. The next one is about pattern recognition, how to recognize patterns that you've seen before and they might indicate some kind of solution that you've used before. Third thing is about generalization and abstraction. And we're going to focus on that a lot because you'll see that most of this is about abstraction. It's kind of what math is. And then the fourth point is about algorithm design. And of course, this is very, very key for being able to write software. The big benefit of using computational thinking, in my experience, is that it really allows people to think about how to take advantage of compute resources at scale. You know, again, Google's pushing this. They work at pretty big scale. So the bottom line is, how can we build applications for big data that have a lot of return on investment? How can we really take advantage of resources like, you know, clusters, tens of thousands of servers in a cluster? So we'll go into that. So step one, decomposition. Actually, let me get to some card deck here. Let me show decomposition in terms of using cards, if I can shuffle these correctly. I've got some nifty airline cards here. And I really did shuffle them a couple times before, just to be fair. But let's deal them out. 5, 6, 7. Okay. I've got 7 cards, and you know they're all jumbled up. If I wanted to count the number of cards that I've just dealt, count the number of cards in each suit, the way that most people probably approach this would be to say, okay, let's put them in piles, one for each suit. So I've got 10 of diamonds here, and I'll put that down. I've got 9 of diamonds. Okay, it goes in the same pile. 10 of spades goes in a spades pile. 5 of hearts goes in a hearts pile. 4, 3, 2. Great. So I dealt out 7 cards. I ended up getting 3 piles. I can pick one of those up and say, I've got 2 out of the diamond pile, and I've got 1 out of the spades pile. And then, let's see, I've got 4 out of the hearts pile. That's a way of decomposing the problem into smaller tasks that can be repeated. That's, in essence, decomposition. So the big idea there is, how do we decompose a task into details so that we can explain the process to another person or to a computer, or even better yet, explain it to ourselves, take some notes, keep them around for later. Okay. Now the next part is pattern recognition. Suppose you're playing poker. I'm going to assume that most people watching have at least heard of a game called poker. I've heard of it. I'm not sure I know how to play it, but that's what I tell people. Suppose you're playing poker with a hand of cards. How do you identify a good move, a good play in the hand that you've got dealt? Well, again, let's go back to my cards here. Let's see. Let's take 5. We'll do 5-card draw. Whoa. Not bad. Okay. I've got a pretty good hand that I just dealt there. If I was actually playing poker, it's not the best, but I've got pair of kings. And I don't know if you noticed, what I did was, as soon as I picked up my cards, I had taken and sorted them out. So I had my kings next to each other, and all the hearts were next to each other. So I kind of got them in order. And that's a way for me to be able to recognize the patterns in the cards. That way I can just look through and say, oh, I got a pair of kings. Maybe, kind of, sort of, if I could really take some risks, I might take my hearts and try to do, you know, well, I could do a straight if I was really lucky. Maybe a flush. So there's a couple different possible moves I could have out of these cards. In other words, how do we notice similarities or common differences to help make predictions or lead to shortcuts? We'll see this over and over again in data. With cards, of course, it's pretty intuitive. Next up is pattern generalization and abstraction. Okay, so suppose that you are playing this game poker with a bunch of other people, some different friends, and the dealer, whoever is dealing at the moment, the dealer gets to choose what variation of poker game you're going to play. Maybe it's 5-card draw or Anaconda or Texas Hold'em, something like that. There could be really subtle nuances in these different games, these different variations of poker. But if you know the basics of it, the kind of things you're going to use over and over, like how to ante up or how to call hand, how to count the cards that are visible across the other opponents. If you know those elements, then you can reapply them to be able to learn a new variation on the fly. If somebody calls out a game that you've never heard of before, you can take that generalization, that abstraction of those elements, and be able to learn how to play it, hopefully how to win it. So in other words, how do we make use of different levels of abstraction to understand and solve problems more efficiently? Okay, and number 4 is algorithm design. Let's pull the previous 3 definitions together: decomposing a problem, using patterns to help solve it, and abstractions to help understand more effectively. So for example, how would an expert poker player be able to write down simple instructions for somebody who is a novice at the game to learn more about how to think about poker? How do we develop a step-by-step strategy for solving a particular problem? And that's the essence of being able to design algorithms. That's the essence of being able to apply these compute resources and really take advantage of some of the advanced math for big data. For a deep dive into a closely related theme here, computational modeling, I definitely recommend this book by Alan B. Downey called Think Complexity, another O'Reilly title. Alan Downey has some great books, and I recommend all of them for background on this material. Okay, next up, let's talk about how much programming do you really need? And so the first question that I get a lot in the workshops is, do I really need to write programs, to code in Python? Do I have to have that background, like having worked for years and years as a Python programmer to be able to get this? And the answer is not really. But the code can help explain more about the math and use cases and the kind of applications we're looking at. So if you have a little bit of familiarity with the code, you can really leverage that. For that matter, you could actually cut and paste from this material, just cut and paste the code into a prompt, Python prompt, and it should work fine. And in the workshops that, physical workshops that I'm doing, that's usually what we do, is just cut and paste a lot of code and see what the results look like. Or another alternative is just simply not a lot, repeating, or better yet, there's a lot of great resources online. And in any case, we promise not to get too complex with the Python code that's in this material here. We'll serve it up in small morsels. I think the largest one is like 30 lines of code. If you want to get started with Python on, say, your laptop, a great way to set it up is python.org. There's download instructions. And for that matter, a little bit more advanced, but I highly recommend something called Anaconda from Continuum Analytics. It's a platform that has a lot more of the installations you typically use for Python all put together, and there's a free version of it. So if you check store.continuum.io, it'll have a number of libraries. NumPy is one of the libraries I'm going to use over and over in the materials here. So I think that Anaconda tends to make things a lot simpler for people getting started. And meanwhile, all the source code that we're showing here is located publicly on GitHub. It's under Just Enough Math gem-video on my account, CETERI. Also, while I'm recommending great books from Alan B. Downey, there's another excellent book called Think Python, How to Think Like a Computer Scientist. And if you want to brush up on Python, I definitely recommend that. Great. Okay, let's move on to A little bit of background on the math, an Algebra 2 refresher. I'm going to be using some examples that are available online, or rather I'll be referencing them. I'm going to use my own examples, but if you want to drill down and find out more about individual topics here in Algebra 2, there's a really great resource online called Math is Fun. And there's several different topics that we're going to cover during this refresher. There's a few key points about those. One is something called associativity, law of associativity. And you've probably heard of that from earlier math, not Algebra 2, but earlier on. But drilling into Algebra 2, definitely we're going to look a lot at linear equations and polynomials. We're going to talk about something called algebraic numbers, solving for variables. Definitely talk a lot about composition of functions. We get to use this in the code a whole lot. And two related notions, one called systems of equations, and then another having to do with linear algebra using matrices. We'll throw in a little bit of probability and statistics. The book in general has a lot more material about some advanced areas of statistics. What we'll cover in the workshop here is not going to go into quite as much detail on that. So the first part of Algebra 2 refresher is the law of associativity. And this goes back to introduction to algebra. You've probably seen this pretty early on in math. I'm going to take three numbers, 2, 3, and 4. 2, 3, and 4. And I want to add them together. Now, addition has a nice property of associativity. I really add two numbers together at the same time, not three numbers together. So I'm going to say 2 plus 3 plus 4. And what I can do through associativity is to put parentheses in here. So that I've got 2 plus 3. Let's say that that equals 5, hopefully. Now, if I were to take 5 plus 4, I can add those together, come up with 9. That's a way of decomposing the problem, really. You've got a string of numbers, and you can chunk them all down and just add two numbers at a time. Now, alternatively, I could have come in here and put the parentheses somewhere else. I could have said 2 plus 3 plus 4, and put parentheses around 3 and 4, and hopefully that comes out to 7. So now I've got 2 plus 7, which also equals 9. And so long story short, I can move the parentheses around. I don't have to worry so much about how things are grouped. I can regroup them on the fly. That comes in really handy when you're working with data at scale. You know, if you've got a billion of these numbers, you may want to add them together in ways that are just most convenient as they're streaming through. We'll see that a lot later. Okay. Next one is the notion of a linear equation as a way of describing a straight line. So, for example here, if I've got, let's see, let me erase this. So for example, if I've got an equation of y equals 3x plus 2, got some kind of linear equation, that really describes a straight line. If I were to graph it, I've got my y-axis here, my x-axis down here, and I've got points. Drawing this equation would effectively draw a straight line through those points. So you can think of having an infinite number of points along that line. Now, if we have an equation to describe a line, we can change the equation, modify it in many different ways, and that comes in very handy. Okay. We can use algebra to express this same equation, y equals 3x plus 2. We can represent it in different ways. I can take and divide the whole equation by 3, in which case I end up with y over 3 equals 3x over 3 plus 2 over 3. So if I simplify that, I've got y over 3 equals x plus 2/3. So that's interesting. Now I could take and maybe move my terms around. If I needed to, I could say y over 3 minus all of this. So minus x plus 2 over 3 equals 0. Just take the right side, move it over to the left by subtracting it. Now, if I simplify that, y over 3 minus x minus 2/3 equals 0. So I've gone from my first way of representing the line down to another way where I've got a 0 on the right-hand side. That comes out really handy later on. But the main thing is that linear equations are very flexible. We could also come here and say that this equation is essentially a function. So if I wanted to, I could say y is a function of x. And that allows me to be able to come in and plug in an x into my function at any point and calculate what the y value is. That's effectively what you're doing if you're writing a function, procedure, method, whatever you want to call it, in some sort of programming language. So if I want to plug in a table here, I could say x versus y. If I've got -1 and I plug it in here, I get -1 times 3. It's -3 plus 2. I end up with -1 for the y. If I plug in 0, is 0 times 3 is 0 plus 2. I end up with 2. If I plug in the value 3, 3 times 3 is 9 plus 2 equals 11. On and on. So arbitrarily, I could take and figure out what's my value going to be at any point on that line. Another thing about linear equations is we can take and put it into what's called a slope-intercept form. So there's a special format that we look at called y equals mx plus b. And the idea there is that when you're describing a line, the b is the intercept. That's where you, let me get a line back up here. The intercept is where the line crosses 0. And then the m part of it is the slope. And the slope is essentially rise over run, so y over x. That's this part right here. So if we can take a linear equation and put it in this format of y equals mx plus b, then we can figure out what these two parameters are, m and b, figure out where it intersects the axis there at 0, and then we can figure out how much is it changing, how rapidly is it changing, by looking at rise over run, looking at y over x. And so we've already got this in the right format, y equals 3x plus 2. Our slope, m, is called 3, and our intercept is called 2. And that gives us a nice, convenient way of describing lines. Sometimes slope is also referred to as a gradient. We'll be looking at gradients a whole lot later on. OK. Next thing in algebra, taking this a little bit further. OK, I want to talk about using multiple equations and multiple variables. So there's something called a polynomial, where you can have different terms that have exponents, they have coefficients, et cetera. I've got a couple examples here. 3x, let's see, plus 4y equals 1. Okay, that's an example of a polynomial. And you've got two different terms here. And you've also got essentially x. X is a variable. It's to the first power. So there's no exponent shown on that. But there is a coefficient 3 and 4 for x and y. If I wanted to, I could have another kind of polynomial that would have some exponents. Let's say 3x squared plus x minus 5. And in that case, I've got these three terms. I've got an exponent, x squared, so I've got exponent 2, and then here, exponent of 1, and here, exponent of 0. And I've got these coefficients, 3, 1, and 5. So I can take a polynomial and break it down into numbers that describe the coefficients and the exponents. A nice thing about polynomials is you can do operations on them just like you would do with numbers. You can add, subtract, multiply, divide, etc. Now, a polynomial is a way of describing a more complex curve, not just a straight line, but let's take this one. Y equals 3x squared plus x minus 5. It's the one we were showing before. If you were to take and graph this, it's going to end up being a curve up like that. So as you start to get more complex kinds of terms here, more exponents, etc., you're going to start to see more interesting shapes, and not just in 2D, it may involve more variables, more dimensions. But polynomials essentially can describe curves. Now, if you combine multiple polynomials together, say you're using addition, you get another polynomial. So in this case, if I were to take 3x squared plus x minus 5, and let's add it to 2x squared, let's see, minus 4x plus 7. We'll take this example. If I add the respective terms together, I end up with 5, 3 plus 2 is 5, x squared. And then I've got 1 minus 4, so minus 3, x. And then negative 5 plus 7 ends up with plus 2. Let me check my math. Aha, I got it. So the idea is that I was able to add these two together to come up with yet another polynomial. And that's really convenient later on. They add together nicely, just like triples. OK, we can solve for what's called the root of a polynomial, essentially figuring out what the values are for the variables. So if I were to take, let's say, x squared minus 5x plus 6 minus 5x plus 6. If I take this polynomial here, 3 terms, I'll set it to 0. I can take and rework this, refactor it into x minus 2, x minus 3. X minus 2 times x minus 3 equals 0. OK, and you think about it. If you take x times x, you get x squared. If you take x times negative 3, you get negative 3x. And x times negative 2, negative 2x. You add this together, and you end up with negative 5x. So let's do that. Minus 3x minus 2x. If I take negative 2 times negative 3, ends up with 6. Okay. So what's interesting now is I've got these two quantities here, x minus 2 and x minus 3, multiplied together equals 0. So I can also say that I can use that to solve, basically saying that x equals 2 or 3. Those are the roots of the equation. If I plug in x equals 2, I get 0 here. If I plug in 3 for x minus 3, I get 0 there. So that way I've been able to solve and find out what x is in that polynomial. Solving these kinds of equations is where we cut to the chase in terms of a lot of the applications. One other point about this, what we've been talking around is something called an algebraic number. So for instance here, the root of a non-zero polynomial with rational coefficients. If I come back here, I've got coefficients of 1, negative 5, and 6. Those are all rational numbers, very nicely behaved. The root of this is going to be x equals 2 or x equals 3. Those are called algebraic numbers. X is an algebraic number. It's something that we're solving for. Essentially, it's the variable. Keep that in mind because that can change later on. A little bit more advanced, there's something called function composition. If I were to take two functions, let's say I've got y equals f of x. Okay, we looked at that one before. And let's have another function. We'll say v equals g of y. OK, so I've got two different functions. I've actually got, what, 1, 2, 3 different variables. What I could say, just for instance, is f of x equals x plus 3. Let's take this case. And let's say g of y equals 2y minus 1. What I can do is take and compose these together. Take the two different functions, apply one to the other. If I want to solve for v, I could say v equals g of y. And I can compose it. I can substitute in y equals f of x. So I can say that this is the same thing as saying that I've got g of f of x. And now if I plug in some values, or rather if I refactor this, taking the whole thing together, I could say that f of x is x plus 3, and g of y is 2y minus 1. So let's plug those in stages. I could say this is the same as saying g of x plus 3. And now if I substitute that in, then I've got 2y, so 2 of x plus 3 minus 1 should come out to 2x plus 6 minus 1 equals 2x plus 5. The next part is about a system of equations. Now, what we've covered so far was a lot of the basics for Algebra 2, but this is where you really start to solve some interesting problems. System of equations is about being able to solve for more than one variable at a time. So suppose we have two equations, two unknowns. The variables are d and t. And so let me write these down. I've got d equals 23t minus 230. d equals 23t minus 230. And then I've got another equation with the same variables. D equals 11t minus 22. OK, so two equations, two variables. That's usually a pretty good start for being able to find a solution if you've got the same number of equations and variables. OK, so let's take a look at a word problem here for this set of equations. We've got Roadrunner, who can run at 23 meters per second. He has a habit of stopping to eat seeds, and that usually takes about 10 seconds. Usually stops next to an Acme trap. And then we've got Wile E. Coyote, who can move at a rate of 11 meters per second. Let's say he's on roller skates, rollerblades, but he's got a rocket strapped on his back, also from Acme. And he wants to go and catch Roadrunner. He wants to spring the trap. It takes him about 2 seconds to spring the trap. So that's the problem. What we want to try to solve is what's the approximate time that Wile E. Coyote takes to move from his secret hiding place to the Acme trap where Roadrunner is eating seeds. What would be the approximate time for that if Wile E. Coyote is just barely going to miss Roadrunner and, of course, probably get caught in the trap? So we've got the system of equations here. We're going to represent the point where Roadrunner and Wile E. Coyote intersect. Basically, they're both moving along different paths. And we've got these equations that describe their movement along those paths. I could describe this better by saying that distance d equals 23 meters per second. And then we've got t minus 10. So we've got Roadrunner running at 23 meters per second, but he stops to eat for about 10 seconds. And if I multiply that out, I end up getting 23t minus 230. And I've got another equation, which is for Wile E. Coyote. He's moving at 11 meters per second and t minus 2. Takes him 2 seconds to be able to spring the trap. So that ends up being same as 11t minus 22. Okay? So I'll just, again, work with these two forms of it. The variables represent distance in meters and time in seconds. Okay, there's several ways to solve this, but the way that we would typically go about is to substitute d as a function of t, substitute that from one equation into the other. And I'm not going to go through all the gory details of it, but if you were to substitute in down here, you would end up with d equals about 169, and t equals 17.33, so about 17. Another way of doing this, though, would be to put it on a grid and say that we've got, I'll do a blue line here for Roadrunner. I'll do a red line for the other. We end up having T and D. We end up having these two lines intersect at a particular point where d equals 169 and t equals 17. Getting back to our problem, we were going to try to figure out how long does Roadrunner take to move from his hiding place out to the trap. It ends up being about 17 seconds, and then he just barely misses catching the Roadrunner. But the notion is this was described by a system of equations. Now, a matrix is another way of looking at this kind of problem. With a matrix, you've got a two-dimensional array of numbers. And so you can think of that as being like a table or a spreadsheet. These are forms that are very, very similar to matrix. But again, with those numbers that we had before, let's say we've got a matrix of 23 and 11, 230, and 22. Okay, so here we've got two rows, 23, 230, and another row, 11, 22. And then we've got two columns. One column is 23 and 11. The other column is 230 and 22. The thing about a matrix is that you can add, subtract, multiply. You can take two matrices and apply different operations to them and end up with another matrix. There's a special case. There's something called a vector, in which case I just have one column. So this could be a vector here. I've got one column, but I've got a number of different entries in it. And you can take and multiply and subtract and add for matrix and vectors together. There's also something called a scalar, which is to say just a regular number. But if I wanted to, I could take my vector here, multiply times 3, and I should end up with 69 and 33. So I can take a vector, multiply times a scalar, or add, subtract, etc. This is all about an area called linear algebra, where you're working with matrices and vectors. Okay, so computational thinking alert here. Back to our problem of Roadrunner versus Wile E. Coyote. We could represent this as a matrix, as a kind of shorthand to represent the coefficients in the system of equations that we had. Let's say I've got a matrix, A equals, and I've got 23, 11, negative 230, negative 22. Okay, so I've got this matrix A, and I've got these four values here. What I could do is come up with an equation A equals, let's do this instead. A times T equals D. So what I could say is I can take that same system of equations, the two equations that I had before with the two variables, and I'm going to represent it in terms of this matrix for my coefficients and my variables here, T and D. Okay, if I was going to do that, then I'd have T equals, let's see, T and 1. So actually, let me use a little bit better notation here. Let's say I've got a vector T, and inside of it, it's got my little variable, lowercase t, and it's also got the value 1. And then I've got a vector D, and that's going to have just my values there. sorry, my variables there, d and d. If I were to take and multiply a times t, this coefficient matrix times this vector, I'm going to end up with something that looks a whole lot like 23t minus 230. And then down here, I'm going to have 11t minus 22. And then on the right-hand side of it, taking d, I'm going to end up with d and d. So I get back to my system of equations, but I can represent it in terms of this coefficient matrix and a couple of vectors. That's another way of saying that my variables here, t and d, those are algebraic numbers. Those are things we're going to try to solve for. So this is a way to bridge from what we've done earlier with algebra into linear algebra. And if we wanted to, we could take and look at this equation, a times t equals d. We could take and move the d over to the other side, set it to 0, and now solve for this equation. And that's really important because what we've done is to abstract out, come out with a much more general way of looking at the problem. In terms of computational thinking, this is a way of generalizing, abstracting. Using just a few matrices, we can take and describe the same problem as opposed to using many different variables. It greatly simplifies the system of equations we have. It means we have less moving parts, and it makes it easier to recognize patterns within the problem. The other thing is that going forward, this provides a way to apply parallel processing. We can take and do the same kind of computations across a large matrix and end up with our results. We'll use that over and over. Next part is just enough stats. So we want to cover a little bit of a refresher on stats, probability and stats. We're not going to use that a whole lot, but it's good background, and certainly within the book, there's a lot more statistics. The idea of probability, just to review, how do we predict likely events? How likely are they to happen either in the future or trying to test something? Can we try to understand how likely were they to have occurred in the past? So with probability, you're looking, again, at predicting things in the future or trying to sort of reverse engineer and understand how likely was something to have happened in the past to be able to make a judgment about it. A couple examples here. What's the probability that Wile E. Coyote finally eats Roadrunner? And we could say that the probability on that is very low. Just give it some number. I just hypothetically pulled the number 0.0001. Now, that's probably not going to happen. But we could take a look at some other kind of process, something that's a little bit more deterministic. What's the probability that Wile E. Coyote, if he happens to be in Las Vegas, rolls dice and gets a 6? So rolls a 6, probability of that is what we would call a uniform distribution. There's 6 different possible values on a 6-sided dice, and if you roll it, you're going to get one of them with a probability of 1 over 6. Probability estimators, they're a little bit less intuitive once you get in more complex situations. Some people probably don't imagine that quite as much, but that's why Las Vegas and other gambling venues have such great success. So probability is an interesting thing, not particularly intuitive when it gets into the complex parts. Statistics is a much broader term. It describes a mathematical body of science about data collection, analysis, interpretation, modeling, presentation, etc. So in terms of a statistical model, let's describe a kind of a process that happens over and over again, such as Wile E. Coyote just missing Roadrunner and accidentally exploding, courtesy of Acme. Wile E. Coyote explodes. We'll put some predictive bounds on that. We'll say that the time it takes from start of sequence until he explodes is time t, and we'll put some bounds on it. We'll say that the expected value of t ranges anywhere from 0.05 up to 1.2 seconds. Now, if you look at the cartoons, it may actually be different, but it's going to be something like that. Mark Twain had a famous quote from a British Prime Minister, Benjamin Disraeli, saying that there are 3 kinds of lies: lies, damn lies, and statistics. And actually, the attribution for that itself is somewhat controversial. At best, it's probabilistic. But we'll take a look at the damn lies and statistics later. If you'd like to brush up on probability and statistics, while I'm recommending Alan B. Downey books, we'll definitely recommend this one too, called Think Stats. It's a really good one. So for the last section of the first chapter here, we've got a case study. We've got a company called foobartender.io. We want to try to make the business examples in the book much more concrete. So we've got this example tech startup. They sell pre-mixed cocktails online. You go and take out your tablet and you look through the different cocktails that are available and you order them, and then those get delivered to wherever you happen to be, courtesy of a drone. It's delivered to your exact GPS coordinates, and it comes complete with an ID check. But we'll use this as a case study for the different business problems that we have here in this workshop. So step one, customers order drinks from a recommender service based on some kind of mobile device. So, I've got my smartphone. Step two, experts take those orders and they mix the drinks using, of course, only the finest and local organic non-GMO ingredients. Step three, customer orders get delivered swiftly, elegantly, and reliably by drones, of course. Parachuting down, we've got customers who are very happily enjoying their cocktails and hopefully order again soon. That's what this startup does. We're going to call it foodbartender.io, and who knows, maybe we'll get VC funding for it.